Hello and welcome back to the Cutting Edge stage at CogX 2021. I'm your MC, Jess Wade, a research fellow at Imperial College London. Please remember to tweet using the hashtag CogX 2021. Next up, we are going much smaller, and to do that, we're going to talk to two of my most favorite physicists. Dr. Hannah Williams is a researcher working on quantum simulation using ultra-cold atoms trapped in focused laser beams. She completed her undergraduate and postgraduate studies at Imperial College London, where she controlled some super cool molecules in two sensors and studied them in a whole bunch of different ways. And she is joined by quantum queen, Dr. Ying Leah Lee. Leah is a physicist, a founder, and a deep tech consultant. She works on disruptive optical technologies which redefine the limits of precision. Imagine self-driving cars that could see around corners, or portable scanners that can monitor a brain's activity. Quantum sensing could make all of these things and much more a reality. Quantum sensors operate at extreme levels of precision by exploiting the quantum nature of matter. For example, using the difference between electrons in different energy states as a base unit. Most of these systems are very complex and expensive, but smaller and more affordable examples are coming online every day. Together, Hannah and Leah are going to tell us about what's real, what's hype, and how quantum sensing will revolutionize a bunch of different technologies. So the format of this discussion is a little bit different. First, Hannah and Leah are going to introduce us to quantum sensing from their perspective. Then I'm going to ask a few questions, and then we'll come over to audience questions in the last 10 minutes. So if you think of any throughout the session in the discussion, please use the Q&A function. So I think probably it's best to go over to you, Leah.
Hi, everyone. So I guess the best way for me to describe quantum sensing is to really talk about the research that I've been doing. So I use light, which is trapped within tiny glass balls or rings. And some of the light exists like a cloud around the ring. And it makes it super sensitive to anything that moves near it, like a proximity sensor. And this is a classical effect, but it can be made to be more sensitive if you use special kinds of light, such as lasers, where the fluctuation in the brightness of the laser is so small, it's at the quantum limit. And the best way to think about that is like the difference between a really clear phone signal and one where you have a phone signal with lots of noise and hissing and glitches. I'm sure many of us have experienced that when we're using Zoom. And really what you want is that clarity. And what quantum sensing offers you is that clarity, the reduction of all that noise. And in the same way that I have kind of a reduced amount of noise in the laser, I can also reduce unwanted mechanical noise like vibrations in the motion of an object as well. And so you can do that without putting the object in a fridge. You can actually use light to cool the motion, to kind of take away the vibrational energy. And if you remove enough of those vibrations, you can start to measure even smaller position changes or the forces that cause changes in position, like gravity. That's how you can do gravity sensing with quantum sensors. So combined, what I tend to study is getting the best sensitivity in both the readout, the light that you're using to look at the motion of an object, and the mechanical response of that object as well. And if you play your cards right, you can start to exploit loads of awesome things like entanglement or superposition, which gets you even more amounts of sensitivity because you're using tricks that classical physics or the classical world just simply can't reproduce.
Incredible. And also making really good use of all of our physics undergraduate training with all of those words. So Hannah, I guess, could you give us a kind of overview of what you work on and how it relates to quantum sensing?
Yeah, so my work is somewhat tangential to quantum sensing. I work on quantum simulation, where I use ultra-cold atoms, which we can set to interact with one another. But the technology that we use and we are developing is really complementary to quantum sensing and could be used in a similar way. So what we need is that the atoms are essentially, they're very stable. A transition within an atom is the same no matter where in the world that atom is, as long as it's the same type. This measurement is going to be exactly the same. So what people want to do is actually use this as a way of sensing something that changes in the environment, for instance. So electric fields, we're very sensitive to electric fields. And in my experiment, that's actually something that we try and control. So we want to try and remove all electric fields, but you could use this same technology to then actually create an incredibly sensitive sensor for measuring changes in electromagnetic fields around, or measuring changes in magnetic fields, etc. And so it's tangential, but it's the same. It comes down to the same technology and the same experimental requirements.
Yeah, that's absolutely fascinating. I love the idea that you can get atoms and molecules to tell us something about the environment that they're in, to sense and to kind of really pick up on fields or something like that. It's really, really incredible. So I guess, Leah, everyone probably in this audience certainly has heard about quantum computing, and quantum sensing is going to be quite a new terminology or concept for them. So could you give me a really brief introduction to quantum computing? And I mean really brief, because I know people like to go on about quantum computing for hours and hours, and then kind of how this sensing technology relates to it.
Yeah, sure. So I think with quantum computing, at the heart of a quantum computer is something called a qubit. And it's basically an atom, or it can actually be not necessarily one atom. It can be like a molecule or even an object, a kind of bulk object. But the key is that object or that particle can be in two states at the same time, which is called a superposition. And you can then utilize that superposition to effectively increase the clarity in when you're doing computational problems. So the way that I see it is like it makes all the statistics and the probability even more enhanced, so that you get the right answer at the end of your problem solving thing. I'm not going to go into detail, but it's quite a lot of effort on actually just figuring out which types of mathematical problems can be solved in that way, because not everything can be fixed with just a quantum computer. And so with qubits, they're really interesting, they're really cool. But I think quantum sensing actually is more than just necessarily using qubits. I think quantum sensing encompasses lots of different things. So, for example, this aspect of superposition, you can use that in a spatial superposition. So you can have an object be in two places at the same time. And it also means that if there's a difference in the environment in those two places, for example, a really subtle difference in gravity, then because the object is intrinsically in both places at once, when you perform matter interferometry, which is when you bring the superposition states back together, they always have to be brought back together. Nothing survives in a superposition for a long time. They eventually come back together. What happens is one of the superposition states has experienced a slightly different environment. And that means that when they come together, you'll get a readout of that difference. And so really, superposition is kind of used to kind of enforce this spatial separation. So you experience different locations, but you can also do things, for example, like ghost imaging, which uses entanglement. So ghost imaging is when you can see around a corner or see past a physical barrier or a wall. And the way you do that is you have light, which produces two photons at the same time. So a photon is like a particle of light. It's a discrete packet of energy. And so if this light source produces two photons at the same time and they're entangled, they're intrinsically depend on each other. The information that's contained within the two photons depends on what's contained in the other one. You can send one of the photons to the object that you want to image, and you can send the other photon elsewhere. It can be like, a mile away, somewhere else, somewhere completely different. It's never, ever seen the object you want to image. And because of entanglement, what you can do is you can produce like a shadow image of the object from the photons that go elsewhere. So you're basically imaging something that the light that you receive has never ever touched, because its entangled partner has touched that image somewhere else. And so ghost imaging is something very real, and it's super awesome. And so those are types of things that I consider very different to how computation works, but it kind of uses similar effects like superposition and entanglement.
I love that. And I also love that entanglement and kind of imaging and seeing your partner miles away sounds like something that would come out of a Gwyneth Paltrow book, but it's actually something yes. that might help in a physical world.
So unconsciously decoupled, yes.
So Hannah, I guess, something I'm really interested in, and Leah's touched on a little bit, and you touched on it in your introduction, but what are all of the advantages of going quantum? Or I guess a better way of phrasing it, are there any scenarios where going quantum actually isn't beneficial, or will everything become quantum in the next 10, 15 years?
That's quite a difficult question to answer, but yeah, so the advantages of quantum technology are really the speed at which things can be done, the complexity of problems which can be solved, and the sensitivity that you can gain. But in the next 10, 15 years, we're not going to all have quantum sensors in our lives. They're not going to really yet be in the general use for the public, but they will be used in things such as, for instance, you can create a quantum sensor that will tell you if there's a pipe underneath the floor that you're about to dig up, which, as it turns out, we don't know where most of the pipes are in cities. So that could be a very useful and impactful application. But you're not going to, I doubt you're going to be driving your car with a quantum sensor that is going to tell you whether there's something coming around the corner at you in the next 10 years. And because these technologies are very expensive to develop, and they're still quite in their early days at the moment. But the future is looking very bright.
I really love the idea that you could use it for looking at pipes under busy streets. We're having in London at the moment, I'm sure you've seen it, Leah, but we're having fiber optic broadband being installed everywhere. And that means that every morning at kind of 5 a.m., you have people going out in high-vis jackets with essentially metal detectors trying to work out what's in all the layers below. But if you had some kind of way of doing that more efficiently and with new technologies, and you could map out a city, it's just kind of fascinating that something that happens at such a tiny molecular level, and we're thinking about entangled photons, could be used to improve urban planning. I would never have imagined that when we were learning physics as undergrads. And I guess that's a really good question. Like, obviously none of this is new science, right? So I wonder, Leah, what you think has changed over the last, in recent years. There seems to be this massive hype and interest in quantum, and what's caused that, what's driven that change.
Yeah, I think it's fascinating too. Quantum has coexisted in our lives for decades. There's lasers. Lasers are kind of intrinsically a quantum process. And so lasers have been in our lives since the 70s, and they've transformed so much of what we understand about kind of fundamental science, but also they're used on loads of things like laser surgery, machining, all sorts of stuff. But then also lasers are kind of like the seed for then creating more quantum behaviors. So in a way, quantum is kind of driving more quantum. And we also have quantum behaviors and transistors and stuff like that. So having quantum in our lives has kind of always been there. But this is like to me, a new flavor of quantum, which is really trying to exploit what some people call like the second generation quantum, which is superposition, entanglement, kind of the more wild and wacky behaviors, which aren't necessarily related to like lower noise or better coherence or faster. We're trying to now really push the limits of these really, really kind of state-of-the-art quantum methods. And what's happened, I think, over the past decade is obviously there's now an interest in the commercial world. So fintech, financial kind of technology sectors, and the financial kind of stock market kind of stuff. A lot of that is driven by having faster and faster processes. So if you can make a financial transaction in like a microsecond or a nanosecond, then you're able to keep up much faster than other people trying to make the same type of deals. So if you have a clock which is really, really precise, so a clock that's much more precise than GPS, for example, and you're syncing your financial investments to that, then in the space of a second, you can actually gain a lot of whatever you call it, gains. I'm not an investor, so you can gain a lot even in kind of like microseconds. And so that kind of fast frequency trading, that's driving a lot of kind of research and innovation in making kind of quantum limited timing sources. And also in terms of security, there's loads of stuff around encryption about how you can possibly break the encryption that enables all our credit cards and all our bank accounts to be safe. And that if you encrypt it quantumly, then that would be kind of the ultimate tier of like the best kind of encryption. So all of that is driving a lot of what's called random number generators, which is when you use quantum physics to produce a sequence of numbers that are truly random, that no one can predict. And so you've got a lot of driving forces from quite traditional kind of capitalist, kind of commercial sectors who are willing to put in a lot of investment, like billions of dollars of investment. And then because of that, you've also got interest from kind of governments, because sensors can obviously be very useful for detecting threats or other things. Encryption is obviously a security thing as well. So it's now become a kind of national interest for nearly, nearly every country now has some sort of quantum program or project, and there's billions of pounds being spent from a government perspective as well. So I think all of that combined has now led to a real explosion of interest, and also startups and investment and all of that stuff as well.
It's completely fascinating. The professors that we had when we were learning physics all of that long time ago were working in this area that had nowhere near the levels of funding and secure positions or sponsorship that they have now. And now that there has been this national investment and kind of global interest, and I guess you're right, it must come from this drive from the financial sector or where you're going to win big. But I do think it's beautiful, Hannah, coming back to your research, that all of those kind of ultra precise, ultra sensitive measurements that could one day impact finance and whatever happens in the stock market that none of us really understand could be influenced by the movement of individual molecules and atoms. And, the study that you get to do really influences so many downstream technologies. I don't know if there's even a question in that, but I do think it's just absolutely phenomenal. And I guess Leah, you kind of touched on it there, but I wonder if quantum sensing poses any of the big ethical dilemmas that seem to plague other aspects of technology, and certainly ones that we're going to be talking about at CogX over the next few days. Have either of you, Hannah or Leah, experienced any challenges in your work, whether that's getting investment, recruiting staff or students, or kind of prototyping your technology? Is there any challenge with it being this kind of quasi-tech that we don't know yet?
Maybe I'll just say something quick, and then I think Leah has more experience in this, but there's definitely a kind of almost national interest within quantum research now. So if you're applying for funding or you're applying for students and you mention that it's quantum technology, then there can be more national security hoops through which you have to jump in order to get people. There might be certain countries where there's maybe some issues with hiring because the UK government or the French government, whichever country you're based in, might not want to share what they consider could be potentially very secret and very important security data, or not data yet, but has potential applications within security that maybe they don't want to share around the world. But that's all. I'm in the academic side, so I think I have less.
No, but it's fascinating, kind of within this highly evolving and super dynamic sector, that you have this, top level in. I guess they're penetrating into the people and the science that we do from the government, and not entirely understanding the research that you're doing, but still having a massive impact on the outcome of it, which is a weird place to be in. Leah, have you experienced it at all with recruiting? I mentioned in the introduction that you're a founder, so I'm guessing that you've recruited some people.
Not yet. So founder, still lean is what we call it. But we have had kind of not barriers, but we've had to work around kind of understanding this aspect of national security for a commercial venture. So, my company, 0 Point Motion, we make optical inertial sensors. So sensors that will allow you to track your acceleration and rotation, so then you can navigate much more easily and hopefully indoors as well. And one of the things that we came across is, in the UK, there are certain limits that in terms of if your sensors are too high performing and they fall under what's called the Wassenaar Agreement, what it means is that you then need to apply for a special export license, and then there's certain restrictions on who you can sell to, and other things as well in terms of who you work with and stuff like that. And so obviously that's a really interesting conundrum for a company to have, which is usually as a company you want to be able to promise even better performance year on year and you want to plan that into your roadmap. But for us, we have a limit. We can't go past the certain performance, otherwise our market shrinks drastically. You're no longer able to sell to like anyone and everyone in the whole entire world. And so what we've done really is to try and this is kind of like 101 how to run a company, I guess, but is to try and align our products to what the customers want. And this is really, I think we've touched upon it in this chat, is there is a difference between what the consumer wants, what someone like a normal person would want in terms of accuracy, versus what a company that's specializing in, looking at whether bridges are going to fall over because the ground is moving underneath them, or like Hannah was saying, looking for pipes underground because you're about to start like a £5 million digging kind of exercise where you don't want to lose that money. And so they have very different wants and requirements. And so what may end up happening is we may end up having to split the company to kind of look at two different types of customers. But for the time being, I think what we've done in 0 Point Motion is to effectively we are not going to cross over that performance threshold, which also means that there's certain aspects of the quantum sensing that aren't needed for those products. So a classical optical sensor will do just fine if you want to navigate indoors, for example. You don't necessarily have to push for quantum in everything. But there are still some markets, for example, space, satellites, CubeSats, who will happily pay much more money for a very good sensor, and they may want that quantum sensitivity if they need to precisely control satellites in space and not avoid each other, for example.
Super cool. I guess on the aspect of super cool, it's so related to what Hannah does. I guess the another interesting thing that's really come out of this conversation is how much optics and photonics are kind of crucial to this quantum revolution. I wonder whether, Hannah, you could speak to how you use optics and photonics in what you do and how you see it changing in the future.
Yes, so the entire experiment that I use is based on lasers. It wouldn't work without lasers at all. And as every few years, the technology of lasers is actually getting better and better and better. And this means that our experiments are getting more and more accurate, and we can have more atoms that we use and we can control them more precisely. And every time there's an advancement in the technology, then there's an automatic advancement within the experiment, but it normally comes at a cost of a few €100,000. So
I love lasers. I love how outrageously expensive they seem for all the innovations that we need experimentally. Every time I'm like, that would be fun. Or magnets. Every time I'm like, that would be fun to try out. Let me just buy that magnet. It's like, oh, it's £25,000.
Yeah. I think
what were you saying, Hannah?
One of the maybe drawbacks of how good we are at this point of controlling atoms and molecules in order to do these fundamental or hypersensitive measurements is that they're so expensive to get into now. So if you want to build a new lab, you need at least £1 million in funding just to be able to think about even trying to build an experiment that's going to be competitive with the ones that are already out there. So that and then realistically, you need some kind of industrial or commercial sponsorship to make that happen, because government grants can't keep supporting the development of these research groups. So actually, one of the things that's quite interesting about this area, at least where I work in, is that the outset cost is huge. So to build an experiment, it's enormous amount of money. But then once you've got all of that, until the next big step in technology, then it's pretty much, well, you have to pay for people, so there's still a lot of money involved, but it's not the same. It's not like we have to rebuy the £500,000 laser system every 2 years. At least I hope, otherwise.
So I wondered, I guess, Hannah, are you interested in translating your technology to commercial applications? So in a way that Leah has done with 0 Point Motion, are you thinking that there might be some long-term plan to take this out of research interests and take it into something commercial?
So actually, the experiment that I'm working on at the moment, my boss has got a quantum startup as well. So this is completely different to what Leah does. It's basically building a quantum simulator using atoms, where the idea is that either people would be able to buy one in the long-term future, but maybe earlier on they'd be able to access it through the cloud. So you will have a physical model that you wanted to run or calculation that you wanted to do. You could actually access this quantum simulator through the cloud and then run yours from wherever you are.
And then the plan with that would be to simulate what you expect to get in reality, and then use those simulations to understand whatever tech you're building.
Yeah, so it's very linked to like material design, so stuff that you're actually interested in, Jess. So for instance, understanding how photosynthesis works, which is very much a quantum mechanical effect, which is basically based on charge transport, which we can model via the interactions of atoms. Would then, if we could understand photosynthesis, we could then actually use that to, or we, as in material scientists, absolutely not quantum, not me, could use this to design like a material that would make very, very efficient solar panels, which would be just taking the inspiration and the way that nature actually works. And then they could be like 90% efficient, which I hear is much more efficient than they maybe are now.
Much, much more efficient. And actually it's really incredible, I think, that now we're having these advances in technology that's supporting the design of new materials for a whole bunch of different applications. It's still very kind of secretive, I think. The governments and the countries that have really nailed the quantum simulation of materials have hugely closed their borders to that, so that we can't understand it. But it's evolving all the time, and it's just a really, really beautiful area of science. So questions are coming in through the chat. So we should start to wrap up our discussion. Leah, how differently do you think what you're working on now will seem or be in the next few years? So if we look forward to 0 Point Motion in 10 years, other than having multi-million-pound investment as a result of your talk at CogX, what do you see as the kind of next change?
Yeah, well, I think one thing that we're definitely pushing is miniaturization. So I'm sure if you go and visit Hannah's lab, you'll see that it's not like a small tabletop of stuff. It's probably a room which has loads of different parts and loads of other tables and rack mounted things and lasers, which are kind of huge and stuff like that. And so what 0 Point Motion is all focused on is chip scale. So we do everything at kind of silicon chip level, using kind of the processes that people currently use to make computer chips. And there's a huge amount of effort, not just by me, but with many other organizations and universities and governments, to accelerate kind of the development of lasers on chip, but really, really nice, high quality lasers. So not the lasers that you would have seen in like CD players, if anyone still has a CD player, but kind of much more kind of brighter, more coherent kind of lasers, which are suitable for things like, quantum experiments and stuff like that. And so it's funny because as a sensor company, we have to not only push the actual sensor part, the kind of interaction between optics and mechanics that I was talking about before, which is kind of my research, but we also have to push all the other parts of the sensor, the laser itself, detectors, signal processing. There has to be a tiny little computer chip inside that does all the thinking and all the processing and stuff like that. And all of that has to be compatible. It's not quite as simple as just kind of ripping apart a standard chip. and just replacing bits of it. Some of it is, but some of it still needs a lot of effort. And so I truly believe in 10 years' time, you're going to see a lot more smaller quantum facing or quantum enabling devices, smaller lasers, much more nicer lasers. You'll see shrinkage in terms of space that you need to start a quantum experiment. I'm hoping you also see a reduction in cost of access, so that these things like lasers, cold atom traps, vacuum chambers, all of that should be getting much cheaper, since there's so much commercial activity driving that, towards products and stuff. So I hope there's more people involved in quantum. I'm hoping there's also more kind of multidisciplinary kind of collaboration as well. So I now kind of encompass like quantum physics, engineering, and also navigation. So I've had to take on a lot of skills in terms of understanding, navigation and trying to bring quantum sensitivity to something like navigation. So yeah, it's a bit of a broad one, but yeah, that's what I hope. Cheaper everything.
I want a cheap laser system. My goal in life is to have all of this at home. So I don't have an optical table, so we're going to have to work it out. So that was absolutely fantastic, and I think I'm going to jump to questions in the chat because there are so many good ones. And actually it touches on your last point, Leah, about kind of diversity of different research areas that you've both had to manage and learn in applying these different technologies. So do you have any thoughts on the use of quantum sensing for healthcare environments? So diagnostics or testings or measuring of vital signs. Have any of you thought much about this?
Yeah, I mean, there's lots of things that you can do with sensing or imaging, but for biomedical applications. So there's loads of sensors out there that kind of use diamond, and inside the diamond there's like a defect. There's actually like a mistake in the diamond where some of the carbon atoms are replaced by nitrogen, and what you can do there is it creates a qubit, so it can be in one state up or one state down, and you can use that to kind of measure really precisely, electric fields or magnetic fields. And so you can do things like brain imaging and stuff like that. So there's loads of startups doing that right now, testing it on kind of petri dish type testing first before trying to do something with human subjects, but they're really promising. So yes, there's loads of applications to do with enhancing imaging for biomedical things. You can do ghost imaging as well for biomedical things, where you use a different color of light for the light that hits your tissue sample, so that the light doesn't heat up and like kill the cells, but you use another wavelength which has much more clarity as your entangled kind of source, the bit that hits the actual detector. So that's two examples.
I think it is quite phenomenal, actually, that innovations in material science, particularly diamond or other really fancy novel materials that are coming online, are giving us this opportunity to really detect minute biological changes with extraordinary sensitivity. It actually links to another question that came in that says, does quantum sensing help from an environmental perspective? Can we do kind of low power computation with it? And it's exactly the same as what Leah mentioned about magnetic field sensing for the brain, that actually if you can detect ultra weak magnetic fields, you can massively increase the information encryption and things like with data storage and computation, and massively decrease the power that you need to use to do all of these things. And certainly that's coming online as we understand more about atoms and molecules and these structures, driven by researchers like Hannah, who really developed the instrumentation and technology to make that happen. So yeah, magnetic field sensing is something I'm super interested in at the moment, and how we can use it not only for brain imaging, actually, Leah, but also for monitoring cardiac function. Basically, anywhere in your body that electric signals, electric currents get sent around, you have a magnetic field associated with that. And the weaker and weaker we can sense those magnetic fields, the more we can understand about our bodies, which is just so cool. So a good question. Does it, and this is open to both of you, does it look like quantum sensing and quantum computing will be complementary to one another, or do they have minimal overlap in the applications? So Hannah, I suppose, do you think your ultra cold atoms are miles and miles away from a quantum computer, or is it a little bit more entangled than I thought?
So we've tried to make this clear, but the actual technology behind the sensing and a quantum computer and a quantum simulator are essentially the same. It's all about better control over whatever your quantum bit is, whether it's an atom, a molecule, a macroscopic device, or a quantum dot, or a superconducting qubit, whatever it may be. They're all sensitive to everything. And in quantum computing or quantum simulation, what you want to do is not be affected by these background changes. So you want to create an environment that is completely isolated. So in a vacuum chamber where you have no other gas present, where you can control exactly the magnetic field and the electric field that you want to apply. You want it to not move because it will be sensitive to gravity. And then by developing these technologies and understanding the way that the atoms respond to other things, you can then directly translate that knowledge into the design of a successful quantum sensor, because by knowing how sensitive something is, you can then know whether it's suitable for your application or not. And by knowing very, very precisely how atoms or molecules or whatever it is you're going to use respond to different environments, you can then know how best to detect the thing that you want to sense as well.
Yeah, I guess then you learn about what your environment is. You have to really do that mechanistic understanding, that structure property relationship stuff first. I was speaking to someone about taking the materials that I work on into doing actual magnetic field sensing for brain imaging, because it combines my love of material science and physics with my father and brother's love of neuroscience. And they were talking about having to have these massively elaborate magnetically isolated rooms to be able to test any of that. I think they're working with diamond and kind of quantum design of materials like that. But that you have to have a completely magnetically isolated room to be able to prove that your material can do what you say it will, way before you get into any kind of downstream technology. So it is just completely fascinating. Okay, a trickier question, I think, probably for you, Leah. Is there a hope for a Star Trek tricorder with quantum sensing? I don't know if you're a Star Trek fan.
I'm not a Trekkie, I'm so sorry.
And I have no concept of what a tricorder is. But
I'm gonna Google it quickly. I'm so sorry. I'm not a Trekkie.
Look at this. Live answering. Tell us what the tricorder is, and you'll have three.
Oh my god! I went to Wikipedia.
Physicists.
Your favorite, Jess. Wikipedia. Science.
One of my favorite platforms. It's true.
It's a multifunction handheld device, performs sensor environment scans, data recording. Oh, okay. It's just like a little handheld, like a scanner, a remote scanner. Okay, let's not say that.
Well then, we can answer that.
Sure. Yeah. So what I would say is I'm going to be tentatively positive here and say something which is kind of like a handheld scanner type function that could be possible. Basically, because of, I'm very confident there's so many people around the world working on miniaturizing quantum devices to the chip scale. So I definitely think we can get the size form down to something that's more handheld for sure. I think it will likely be a photon, a light-based quantum device at the first instance, because light is much more easier to control. And we're getting some amazing kind of quantum light sources being commercially developed. Whether or not we'll have kind of cold atoms like the ones that Hannah works with in a handheld device that like a normal person can hold and use around, less sure about that. However, there are kind of hot atom devices. There's things called CSACs, which are basically like atomic clocks in chip form, but they're not ultra cold ones, so they don't have kind of full quantum behavior because they're hot. But those are sold around the world, so potentially we could get closer to something that's a bit more of a cool cold atom type thing. but the amount of control that's needed to take something that's like a hot vapor cell full of atoms to something that's a cold atom experiment, that might not be able to be, squeezed into a handheld device. The sensor head maybe, but then you might have like a little rack nearby that contains all the control elements, because control still takes a lot of effort in terms of circuits and amplifiers and special electronic kind of boxes and stuff as well.
I completely feel you about the miniaturization side, even just those kind of handheld spectrometers. I think like, wowee, that's the coolest thing ever. But then also having visited Hannah's lab, I cannot physically imagine getting any of that down to a handheld scale. But it will come. And I think actually something you touched on earlier, Leah, about kind of pushing from the space sector, the space sector has the money to really push for these developments, and they also have to think about compacting it, but not only compacting it, but also about the environments this kind of technology will be in. So one of our colleagues works on the NASA Mars mission, and they're thinking about building these hypersensitive spectrometers that can operate at -20 and +250 degrees, can be transported out to Mars. So really, I think that kind of push and that innovation and discovery is coming, and it's happening. And well, I'm just very glad that both of you are leading the way. So thank you so much. I don't know if you had any other aspects that you want to touch on, but I would say everyone who's enjoyed this conversation or is more interested in hearing about what 0 Point Motion and Hannah and Leah go on to do in the next few years, follow them on Twitter, keep asking questions about quantum sensing and quantum technologies, and they will definitely get back to you. Do you have any parting thoughts, or do we need to leave you to go and build the next quantum sensor?
I think I just want to encourage anyone and everyone, if you have an interest, to get involved, because I think quantum, it should be a career that's open for anyone at any stage. If you have a history in working in mechanics or something, step into quantum later on in life. We need loads of help from industry and from users and from people who actually care about the thing that we end up wanting to measure in the end. So yeah, and also, kids, students, don't be afraid. It's not as scary as it might seem.
Everyone loves quantum, Leah. I think you should meet all the undergrads. All they want to do is talk about quantum.
Really? That wasn't what it was like 10 years ago. But okay.
Favorite lecture course. Hannah, anything from you?
No, I think Leah pretty much summed it up. We can't just trust quantum physicists to solve all of the problems in the world. We need input from people with experience in other research areas or not research.
And yeah, it really complements what we were saying before, that the science isn't new or intimidating. We're just learning new ways to apply it. And actually, that's going to take a whole bunch of different ideas and people to make that happen. So with that, I want to say thank you so much. Have a fantastic rest of your day. To everyone who is joining, whether that's in person or whether that's virtually, no one's in person in our bedrooms and living rooms, I promise that. But everyone who's watching virtually, thank you so much for joining. And we will see you later on today for some more fantastic discussions around cutting edge technologies. So have a great lunchtime and have a great afternoon wherever you are.